Okay, so I think a lot of people are joining just now. Let's kick it off. So hello, everyone. Welcome to the first of the webinar series by Kraft Prospect in collaboration with QURECA and partnering with Astro Agency. I'm your moderator today. So my name is Bettina Hein, and I'm currently the Business Development Executive at Astro Agency, which focus on marketing for the space industry. I have previous experience building satellites and have conducted research in deep learning applications for space with the aim to develop a system for on-orbit data processing. So this webinar today is powered by QURECA, which is a startup that fills the gaps in the existing quantum community. So thank you very much, QURECA, for the opportunity to use your platform for this webinar. Today, we will be discussing quantum technologies in the space industry. That is the applications of quantum mechanics for a technology used in the space sector. When we think of quantum mechanics, we can now go back 100 years, when in the 1920s, Schrödinger formulated his famous equation. Even though we use quantum mechanics every day in lasers, transistors, or magnetic resonance technologies, imaging, it is just in the past 20 to 30 years where we have seen some major advances in quantum technologies. And in the last 10 to 15 years, we have started to see the application of quantum technology in the space industry, which is even more mind-boggling. We are now entering the so-called second quantum revolution. In the UK, Kraft Prospect is a space engineering company which deals with novel applications of quantum technology on CubeSats. Kraft is currently leading a consortium for one of the first quantum key distribution payloads on board a CubeSat in a demonstration mission called ROKS. There are currently multiple missions planned around the world launching satellites with quantum payloads on board, both space agencies as well as companies. And today, we are thrilled to have world leaders and experts on this panel actively involved in developing quantum technologies for space and in leading some of these missions. So moving forward, I'm going to introduce each speaker and invite them for a short introduction to their work. Our attendees can post their questions on the questions tab during the talk, which we'll be taking up a little bit later on in the panel discussion. So for our first speaker of the day, it is Professor Thomas Genuine. Thomas is a faculty member in the Department of Physics and Astronomy and the Institute for Quantum Computing at the University of Waterloo since 2009. His research is focused on experimental implementations of quantum photonics and quantum optics, foundational questions and experiments of quantum entanglement in quantum science, and in particular, performing quantum communications between ground and space. He is the principal investigator for the Canadian QEYSSat mission proposal. So thank you, Thomas.
Oh yeah, well, thank you very much. Thanks for having me on the platform today and allowing me to introduce myself and my work. Thanks for the great introduction. For me, it's a very exciting time, I will say. I'm an experimental physicist. I've been working towards quantum in communication to space for many, many years actually by now. So I was still a PhD student in Vienna in around the year 2000 when we first started to get engaged in some activities with ESA actually and looking in early studies and so on. And since then it's been quite an endeavor, and it's amazing times now to see this activity become pretty much a mainstream activity with so many missions and projects going on everywhere around the world, right? And of course, as we all know, right, the Chinese group has been leading a lot of these activities also recently, but it's just an amazing time. So my own interest and work for many years has been this long distance quantum communication. The big vision for me is one day we'll have a quantum internet, and satellite links will be an important piece of such a quantum internet, and that is why I'm so interested and fascinated about this work. And it's a great honor to be leading a project here in Canada, the QEYSSat, quantum encryption and science satellite, which will primarily put a quantum receiver into space and receive signals sent from the ground to space. So yeah, thank you very much. I'm excited to be a part of this discussion today.
Thank you. That was really interesting. Thanks. So next up, we have Dr. Bettina Hein. So Bettina is currently working as a systems engineer in the pre-development department at OHB System in Oberpfaffenhofen, south of Munich, focusing on early phase projects in quantum technologies. She is a founding member of the Quantum Technologies Working Group at OHB, with a particular focus on business development in the framework of quantum communication. She has a background in the implementation and investigation of various quantum communication protocols, in particular for atmospheric transmission, and has been an active member of the OSA for many years. Thank you, Bettina.
Well, thank you so much also from my side for the nice introduction. So actually, I would just like to pick up what Thomas Jennewein already said, that I also have been, maybe not so long as him, but also working in the field of quantum communication for quite some time, as he said, during my PhD time. And also I happened to spend a couple of months in Thomas's group where we worked together on a free space link as well, which was a really interesting time for me as well. And yeah, as you said, meanwhile, I am working for OHB, and OHB, for those who do not know the company, it's a large space system integrator that is based in Germany with two sites, one in Bremen in the north of Germany and one in Oberpfaffenhofen, which is a bit out of Munich in the south. And within OHB, we have all different kinds of topics, and OHB really covers a whole broad range from really large scale projects that we integrate, but also we do technology development for selected technologies. And part of the areas, for example, is telecommunication, navigation, but also science missions, Earth observation. And since around 2016, we tried or looked deeper into also quantum technologies. And for that, as you said, founded the Quantum Technologies Working Group, where we basically identified three major topics to be of interest. That is quantum key distribution or quantum communication in general, then code item sensors, and atomic clocks and frequency comps. And in my basically, or my, well, daily basic, working basic, I focus on the quantum communication part, and I lead a couple of studies that we are involved in on quantum communication. And one is also connecting to what Thomas said, based on the vision of a future quantum internet. We are leading a study, or we are part of a study on the quantum communication infrastructure that is currently going to be established by the European Commission in cooperation with QEYSSat. You may have heard of that. And we are part of one of the consortiums that look into detail into the potential user requirements and the first architecture on that. And I'm happy to go deeper into detail if you're interested in that. Thank you.
Looking forward to it. Thank you for that overview. So our next speaker is Doug Mcneil from Kraft Prospect. Doug has significant experience within the systems engineering domain and is the current head of systems at Kraft Prospect. He has been working on the ROKS project since inception, undertaking initial feasibility work, which was a precursor to the current mission opportunity. Doug spends most of his days trying to grapple with the requirements of space, cybersecurity, and quantum.
Perfect. Thanks very much for the introduction, Martina. So yeah, that's a good overview of what I do. Just a little bit about Kraft Prospect as a company. So we're an SME based in the Glasgow area, which has kind of become a hub for nanosatellite manufacture in the UK and also globally. At the moment, we're currently sitting around 13 in terms of headcount and a third year of training, and we've seen sustained growth kind of since the company's inception. In terms of what we do, predominantly commercially, we are a mission service provider, and we focus on systems engineering and in particular on nanosatellites. And the thinking behind this business area is that there's a lot of kind of novel ideas that come out of, say, universities, and people may not always have the expertise required to deploy these on nanosatellites. So that's something that we aim to provide support with. There's a few companies operating in this domain, and within this, we kind of aim to differentiate ourselves by investing in internal research and development. And there's two key areas that we investigate. First of all, something we call responsive operations, and everyone else calls autonomy. So as part of this, we are aiming to increase the overall autonomy of satellites to reduce the operational cost, and that's where we see our margin being made. Within this field, we've got a number of kind of core areas of IP, one of which is deploying lightweight neural networks on low size, weight, and power hardware for things like cloud detection. And also we're increasingly interested in the assurance of autonomy, making sure that implementing autonomous architectures isn't going to impact on the overall mission. Our third kind of area of the business, which is most relevant here, is something we call novel missions. And within this sits all of our work on quantum key distribution. And as you already pointed out, Martina, we're working towards a demonstration mission for QKD from NANA satellite. We're also looking in the longer term to develop services in this area. In terms of the projects that we have running in this area, we are looking at things like weak coherent pulse BB84 QKD payload for a nanosatellite, secure computing to make sure that there's not an attack vector for hostile actors through the satellite platform itself. Also looking at quantum random number generators and which of the commercially available units is most suitable for deploying on spacecraft. And finally, we're also looking to engage, which is kind of a key part of what we're here to do today. So I just want to finish by saying if anyone sees any overlap between their work and ours, we'd be very keen to talk that through, particularly now that conferences seem a distant memory. So thank you very much. I'll pass back now.
Thank you, Doug. That's all super exciting what you're working on with Kraft Prospect. Looking forward to seeing how that develops. So for our fourth speaker, we have Eamon Murphy. So Eamon is the central R&D and engineering contact point for all development issues related to components, subsystems, and systems for optical atomic quantum sensors in the fields of magnetometry, interferometry, and clocks at QEYSSat. He is the engineering coordinator of the C-Cool initiative in ESA, for which full end-to-end system development shall lead to an integration of complex quantum systems preceding a dedicated space development program. He has worked on the laser systems for first Aeolus and then the Bepi Colombo flight projects, both of which are now flying. So let's hear some more from Eamon.
Well, thank you very much, Martina. Very elaborate introduction. Principally from the time I'm now 16 years, 20 years in ESTEC, and things have developed quite a lot since we came, or since I arrived. But principally, the one common theme right throughout my time there has been development of ultra-stable lasers. But these ultra-stable lasers in the past 10 years, as Bettina well knows, have been making enormous strides, and that has led to huge potential, not only in space eventually, but also principally on the ground first. And so we have attempted to define a sort of a roadmap in the engineering directorate, so that we could support any potential projects, whether they be in Earth observation, so Earth science, fundamental physics, navigation. Those are and also, of course, the ISS implementations on the ISS. So what we have and what I've been focused upon would be applications in atomic sensors, principally. Those would be atomic magnetometers, so basically CPT, rubidium sensors, optical standards, where now the frequencies are now in the hundreds of terahertz, cold atom interferometry, so system studies, mission studies, technology developments, and of course the metrology to try and verify that all these developments are actually achieving the claimed performance at the end of their projects. What came out of this metrology was, over the last 15 years, was in fact comparison between ultra-stable developments between, for example, in this case, MPQ in Munich and PTB in Braunschweig. So this was only, ESA played a very small role in this, but it was instrumental in establishing the fact that we do need to have a proliferated fiber network to compare or to connect the national metrology institutes across Europe. Quantum communication, of course, I'm sure by the end of this hour, we will see that quantum communication is going to be the one that will get the most attention. It's heavily dependent on space infrastructures. The ground links, which were mentioned by Bettina, the so-called EU1 of the quantum communication infrastructure, the saga, it was the QEYSSat part, or the space sector, or the space element of the whole system. And the ground links, which are also vital, as I just said. The EU and the QEYSSat combining is a very important aspect to the quantum communication aspects. And in particular, the Skylight program is the one that's driving all the activities in this regard. Quantum communication for QEYSSat, we can say that it's when the quantum computers are available, they can be used. We will certainly find uses for them. In fact, there is something which might interest Thomas. There is an open ITT very soon on quantum computing techniques for system engineering and spaceflight, which we'll come to later on. And the simulation, those are the 4 pillars which were identified by everyone as being encompassing everything that's relevant to be discussed. The simulation, though, whether it's based on trapped ions or lattice-trapped neutral solutions, actually shares a certain amount of commonality in the development on the atomic sensors. So that's, I would say, concludes what my interests are. Thank you, Martina.
Okay, thank you very much. That's really interesting. So for our final speaker of the day, we have Dr. Mamata Rapa. So Mamata is the technical lead on the quantum key distribution spacecraft and has worked on ESA's Sentinel-4 test campaign in the past at RAL Space. She has worked on transceivers for ExoMars and lunar polar sample return projects while at Kinetic. She has a PhD in software-defined radios for multi-satellite communications from the University of Surrey. She was the systems engineer for StudsAT-1, India's first pico satellite, launched by Indian Space Research Organisation. Mamata is one of the Women in Aerospace UK committee members. In addition, she was the crew commander of Crew 174 at Mars Desert Research Station. Okay, Mamata, thank you. Not sure we can hear you. I think we might have some technical difficulties with hearing you, Mamata.
Hello?
Yeah. Yes.
Okay, perfect. Sorry. Yeah, thank you for the introduction. I'm from RAL Space, which is part of Science and Technology Facility Council. We are based in Harville. We are involved in more than 210 missions with NASA and ESA, the recent one being the Solar Orbiter. We had our instrument there called SPICE, which was launched in February 2020. We also provide facilities. We have ground stations, and we work on a wide range of missions and instruments. This is a particularly interesting mission because it's an international research-led project between National University of Singapore and STFC. So just to give a background to the viewers, we use encryption methods in our day-to-day lives, and they are based on the algorithms such as RSA, which are based on prime numbers. So we encrypt the message using prime number, multiplied number using prime numbers, and then we decrypt it using the prime numbers. But it is indeed difficult to identify what these prime numbers are if you're not the intended person. So, but with quantum computers coming along in the near future, that could be possible. And that is when the quantum key distribution becomes really important, because it's a secure communication method that enables two parties to generate a shared random key that's known only to them to encrypt and decrypt the messages. And the uniqueness of this is it allows two parties to detect the presence of the third party if they're trying to gain the knowledge of the key. The primary objective of the quantum key distribution project that we are working on is to demonstrate the entangled photon distribution and also the principle of entanglement-based QKD from space to ground. So this involves entangled source and detectors, one on the satellite and one on the ground, which National University of Singapore is responsible for. And we provide the optics that supports the transmission and reception of the photons, along with the satellite bus and both RF and optical ground stations. So at the moment, we have completed our preliminary design review and moving towards critical design review.
Okay, thank you so much, Mamata, and thank you to all of the speakers for sharing your work and details of exciting missions that you have coming up from different places around the world as well, and various expert perspectives. It almost feels like we are on the threshold of heralding the future with all of the quantum technologies that are appearing and the developments. So, without further ado, I would now like to throw this panel an open question. But before we dive into that, there are a few ground rules for ease of communication. So I'll be taking questions posted by the audience once I've asked a few of mine and directed them to the speakers. So please make sure to click on the Ask Question tab, and then there should be on the right-hand side where you put in your questions, and then I will be able to see them here. And then the first speaker to raise their hand physically, so we're not using any icon or so, will be the first one to be called up on stage. So once I ask the questions, it's for up to any of you to raise your hands to participate. And to kick off the panel discussion, here is a question from my side. So what do you see as the impact of quantum technologies in space? Do any of the speakers want to start off with that one?
Okay.
Yeah, go ahead, Mamata.
I can go that. So because we are involved in the entanglement photon distribution from space to ground, so basically, so I'll speak from the mission that we are working on. So these photons are quite weak. So if we try to transmit them using optical cables or so, we would have a lot of losses. So it would be really difficult to come up with the K. So what this means, it'll limit the distance that we can go terrestrially. So it could be hundreds of kilometers. But if we did it with using space, and free space would surely help this, and we can travel more distance. And therefore, having a secured node as a satellite in space would really help in creating the keys. And these keys can be generated from different places across the globe from using just one trusted node. So, for example, we are working with National University of Singapore, and we also have our own ground station in the UK. So we can generate independent keys using the secure node, which is satellite in space.
Okay. Do any of the other speakers want to add something to that? So I see that as a pretty emerging trend right now. And there was actually someone in the audience, Ankit Kumar Mishra, who asked, what are the emerging trends recently going on in space quantum technologies? Do we see some other emerging trends? Perhaps Doug wants to talk a little bit more about the quantum key distribution.
Yeah,
your projects there.
Yeah, thank you very much. Yeah, I think in terms of emerging trends, yes, obviously I'd like to focus on quantum key distribution, but I think there's quite a few. So I see quantum technologies as enabling across a number of different applications. Obviously there's advances for gravimeters, clocks, etc. So timing and navigation is obviously a big area which might also see growth. But yeah, I think quantum communications and quantum key distribution for some reason seems to grab most of the headlines, or does at the moment. In terms of the impacts on this, yeah, like I say, I think it's enabling. So I'm kind of more focused on commercial services, and I think in terms of the commercial services that we see, we think that quantum key distribution will enable more secure communications. And it's kind of important to frame that as well. So your data is not only valuable at the moment, but it's also valuable in the future. So some of your data, let's say your health records, is valuable maybe 10, 20 years from now. So it's important that we look towards more secure methods for managing data at the moment.
All right, thank you. Thomas, did you have something to add to that?
Yeah, thanks. So I'm actually very excited about the possibility of using quantum links with satellites to extend larger distances. It was already mentioned earlier that terrestrial links are limited in range because we're at the single photon limit. So that's where space at the moment, space technology is the one technology we have, and which is already demonstrated that can reach, thousands of kilometers or even global distances. And so the quantum network, though, in the future, we should point out, won't be just satellite links or just ground-based links. I think the vision is that it will be a combination of, or a hybrid system of various links made up of shorter range and long range links. And the satellite systems would be the one resource that provides this long range bridge between, let's say, a citywide, a metropolitan area type of network, which might be fiber optic probably, but then there might be ground stations just outside of a city, which are still in reach of a fiber optic link, right? A fiber optic link can, let's say, 20 kilometers or something is feasible. But that's already far enough from a city to set up a nice ground station. So, and so I think the vision would be that the quantum links with, links with quantum satellites will provide the long range backbone to enable really far, transcontinental or even intercontinental quantum networks for various applications. I mean, the secure communication is let's say the first application that is the really obvious one, and it's very exciting to see commercial activities in this direction, right? There's a lot of industry looking into it and startups forming up, including here in Canada. We also have some startup in this direction. So that's exciting, and I'm sure we'll see a lot more towards these commercial services for QKD in space. But on the longer range, longer term perspective, it's also still very exciting, like entanglement distribution, which can be used for various applications, right? Metrology, improving sensing, or maybe one day when we have quantum computers, they'll be interfaced using quantum entanglement. And that's where long-range satellite links will come in.
Okay, so I was actually going to ask about that. So the range, of course, space is a whole different range, but now we've only seen a few developments for these kind of space technologies. So what are the current challenges that we see right now? What do we have to develop more? You mentioned quantum computers. Maybe someone else on the panel has some ideas of what we need to focus on more in order to make this a reality.
So maybe also just to add to what Thomas actually said, this is exactly also how the quantum communication infrastructure that is intended for Europe is placed, or is planned. Actually, you will have the terrestrial links for the shorter distances, and then the idea is to have the space segment that is covered by QEYSSat, that will serve as an interconnection of these terrestrial islands. The idea is also to have combined the national activities. So many European countries also have their individual activities on having their own national counterpart of a quantum communication infrastructures, also with many terrestrial test beds and links interconnected, and then overall connected by satellite as well to interconnect these longer branches. And as Thomas also said, so the very first idea is to provide this quantum secure application, or to the possibility to provide secure communication by keys generated by quantum distribution. But on the longer term, the idea is really to have this quantum information network that can serve as or serve for the distribution of resources, such as share entangled photons at different stations for various applications actually. And in terms of the impact, there's of course for the near term visualization, of course, there is the increase in security, the option for quantum safe communication also in the future, in particular for governmental institutions, for data centers, for all these areas where really long-term security is required. But on the other hand, while we are now shaping the trends on and create or identifying also the needs on technology development in the that is still necessary, in particular in Europe, for this infrastructure, we are identifying also other areas that can be enabled by that, or where quantum technologies can be an application. So, for example, for the classical optical telecommunication, also satellite communication, the terminals that are already existing can sort of be used also for the QPD or well, entangled photons transmission, and then that is another also that there is actually a business area that can also be supported by that.
Okay, thank you. So on what you were mentioning earlier, Joshua Anthony had just a quick question on whether you could explain more about the photon-based entanglement process and the corresponding nodes within QKD and space-to-ground-based communications. Bettina, do you want to answer that one?
So, sorry, was it to me?
It was an open question to anyone on the panel. But Mamata, go ahead. You can answer that one.
Okay.
Yeah. Sorry. Yeah, I'll let Doug go first.
Yeah, I'm not sure that I'm the best person to answer this. I think this potentially might be a physics question. But yeah, my understanding is that essentially in the quantum internet, the entangled photons could be transported almost physically through satellite networks to other points. Yeah, potentially, Thomas, are you able to take this on? Sorry, I'm backing out as well.
It's a good question.
So yeah, if I may, so I'd just like to recap what I understood the question was about is how will entanglement be used in a satellite-based network? I think that's kind of what I understood that the question was about. So my perspective is that entanglement has a very unique feature that could make it very useful for, secure communications. So for example, if there's a source of these which produces these entangled photons, they come out with this quantum correlation. And then the two photons could potentially travel in various different directions and be measured at different sites. And in terms of, let's say, key security for generating a secure key, the source itself does not, in principle, have to be secured or trusted. So it allows to build, if we just think of a QKD network, it gives us quite a bit more flexibility in such a network topology, right? You could have a satellite which has an entangled photon source, and the two photons are sent to in opposite directions to two different ground stations, and this would alleviate some of the security concerns you may have on the spacecraft itself. Or I could have a ground station where there's an entangled source at the ground station, one photon goes to space, and the other one travels in fiber optic to the nearby city. And that's the scenario where, for example, our QEYSSat, the receiver in our QEYSSat system, could be very well suitable for. And again, I would not have to trust the ground station facility as much as I would have to if it was let's say a weak coherent pulse type of source. Now that's more like in the near term. In the longer term, I think entanglement distribution will be essential for building this quantum internet, and indeed various groups are already looking into hybrid quantum repeater topologies where you have, a quantum repeater is actually is kind of an unfolded quantum computer which has memories and a small processor which can share entanglement and then distill out of various entanglement links, can distill a better entanglement with higher quality and also correct errors. And I think that's our biggest goal. Now, again, there's still, in a quantum repeater, there's still this terrestrial link that's needed. And in papers, we've been able to show that by replacing these links with a satellite link, which can be much longer than a ground-based link, one can actually also build a repeater at a larger scale. I should say a quantum repeater. And so I think that's, again, why quantum entanglement will be essential. And also, if I think of doing intersatellite, networks that involve intersatellite quantum links as well, I do believe quantum entanglement could play a really interesting role. Again, I could have a source and send one photon to ground and the other one to another satellite, for example. So there's very interesting scenarios that could be considered.
Yeah.
Just adding,
sorry.
Just adding to that point of Tom, so what we are doing is we have the entangled source that's on the satellite, and there is detector. One of the detectors is again within the satellite itself, and the other one is on the ground. So if we call them Alice and Bob, Alice is on the satellite and Bob is on the ground. And then what happens is they don't share any data that's been transmitted because they use random bases to measure these photons at both ends. And therefore, only the information of the base that they've used to measure is sent from one person to the other person. And they just compare the bases and say, okay, position 1, 10, and 20th are right, and I use the same basis. So based on that, then you can detect whatever data that has been encrypted from that is valid or not. And then there is a quantum bit error rate that has to be good enough to get the key information. And then that's how usually it's done. So it could be done either on the satellite or on the ground, or as Tom mentioned, on 2 different ground stations.
I love that analogy with Alice and Bob. I've heard that one before. Another interesting part of this, an interesting aspect, is quantum internet. So we had someone in the audience ask what the missing links to real quantum internet is and what we need to do what we need to invest on. Perhaps Iman, you have something to say about that?
Well, the quantum internet is a project on which Bettina is working. So I guess that is as the QCI, or the quantum communication infrastructure, is one element of the so-called quantum internet. But I think what's at the root of the quantum internet is being able to share two disparate systems, whether they be a quantum processor or two communication signals, using what's in one way is an infrastructure which is already there. Of course, you cannot think about or cannot assume that the fiber network, which I mentioned at the start, which is already there for conventional comparison of frequencies, very high performance, so coherent links, because the major difference then would be, while we could live with a bidirectional link for high performance frequency comparison, this is not necessarily the same with communication protocols where you're comparing possibly quantum computer or quantum processors. And you still have the issue of the length limitation because of the issue of loss in the fibers. You also need perhaps a quantum memory to boost the signal, but only in certain limited over certain limited distances. The major difference between what I would call a conventional fiber network for comparing clocks or signals, even at carrier frequencies in the terahertz, hundreds of terahertz range, with the quantum internet is basically the length and the fact that you don't have bidirectional possibilities. And but this is not the people who are working on this now. There's a European quantum flagship program which is headed by TU Delft, and it's running now a year. I would be very curious to know what the results coming from that study actually are, because in essence, if you have a network of comparison of high performance clocks, which are there to provide the reference, the steering reference to Galileo or to GPS, those same national metrology institutes are highly secure locations. So the point then is, could one extend this network, not the network physically extend it, but rather extend the philosophical use of the network for a quantum internet as well? Because then you would already have the security issues which are already there for the national metrology institutes, which have as an implicit element a security issue, because they're already participating in timing for Galileo or GPS. And I would be surprised if the project, the QCI, was not going to look in this direction. or what's more generally the quantum internet, because the quantum internet is you can put different explanation on it as depending on your preference, but whatever quantum device you have at A, you would like to transport it to B, and that's the quantum internet as I see it, and as I would like it to see it as well.
Okay, thank you. Bettina, do you perhaps have something to add to that? Bettina, do you have something to add to that, since you've been working in this area?
So I'm working in the area. Actually, we are not working in detail already on the quantum internet, because I think it's still quite a long way to get there. So maybe also the most important thing when comparing conventional networks, fiber networks, but also satellite-based networks with quantum networks or potential quantum networks, is the fact that quantum states are very fragile and they are very sensitive to losses. So the problem is that you cannot, for example, in terrestrial networks, transmit the quantum states for longer than, say, I think the most the longest distance so far was something like 400 kilometers, but that is really the yeah, not so easy to achieve. So currently we're only talking about like 100, 200 kilometers or so. And for that, as Thomas said, you would need repeaters, quantum repeaters, but they do not really exist in a very mature way already. So you cannot amplify yet your quantum state. So for extending longer distances, then you would need these repeaters. And this is certainly a major part that also would be required for a quantum internet, because you would, of course, like to extend the lengths, or having a longer length is achieved than only like hundreds of kilometers. That is one part, and the other one is also that you would require quantum memories, which are also not yet that far matured in their development. And then so the idea that is to do individual development step by step towards that quantum internet, and for, as I said, for the quantum communication infrastructure. So the idea in the first step to do this quantum secure network opportunity is trying also to look into architectures that already include entanglement-based schemes, then that could in the first place be used to transmit or establish shared keys based on the correlations that provides entanglements, but then at a later point also could be extended to well, longer distance entanglement distribution that you would need for the quantum internet. And as also was said before, so for another option for extending length limitations by terrestrial networks, so far, as long as you do not have repeaters, there of course satellites can play an important role, but because they can also offer the opportunity to distribute two pairs of well, entangled photon pairs to do distant ground stations.
Okay, thank you. On the topic of quantum repeaters, we had Tomek Schultz from the audience ask how many quantum repeaters on an estimate would be necessary for a worldwide quantum network.
This is I'm happy to try to answer. It's a tricky question. Yeah. So we had a paper in 2015, I believe, where we modeled a scenario, and it was something like a global network, meaning, you know, from connecting two opposite directions on the Earth, and points, I should say, and it was something like 8 satellites, so 8 satellite links with entangled sources and the corresponding ground nodes. So it's exciting. I know it's hard enough to get one satellite into space, so I know it's tricky, but it's also not 1,000, right? So it's actually exciting. But I also would like to say this was just one study for one architecture, and indeed I'm aware colleagues are looking into alternative other architectures that might be more, let's say, more better scalable or more interesting.
Mm-hmm. Okay, so actually on that point with satellites and leading into constellations, we had Ebbe Borg was asking, where do you see the role of mega constellations such as SpaceX, Starlink in the future of quantum internet?
Doug? I can take that. So yeah, I think based on our analysis as well, the potential for mega constellation is probably a bit much at the moment. Coverage can be achieved using a lower number of satellites, and in particular for lower data rates. So, for example, for quantum key distribution applications. So, there obviously is potential, but at the moment, I think that there's smaller steps that can be made, and as Thomas has already mentioned, with a lower number of satellites. So, the actual key management problem itself is a multifaceted one, and part of the benefit of using satellites is that they provide a separate channel for the provision of data. So that's very important to mention. So yeah, some of our works look at kind of coverage, and the maximum that you might require is in the kind of hundreds for global coverage, and that's using nanosatellites at those kind of data rates. But of course, it depends on the application and how many keys a particular application is using. Our research tend to focus on applications which require lower amounts of keys, so niche applications. So going back to something we've talked about earlier, we tend to focus on augmenting other systems with nanosatellites. So looking at how nanosatellites can be used in conjunction with constellations of larger satellites. So in conclusion, I think that what will emerge is kind of a multi-domain service. I think that's been a theme already. So multi-domain service featuring larger satellites, nanosatellites, HAPS, and obviously ground-based networks. So I think the likelihood of a mega constellation for this particular application is at the moment unlikely, but obviously that's something that as the quantum internet emerges, then that might change in the kind of medium to long term.
Okay, thank you. We had someone in the audience, Robert Hadfield, was asking, what is the optimum transmission wavelength, which goes a little bit into this discussion with constellations as well. Do we have anyone on the panel who wants to have a stab on that? Yep, Thomas?
Oh yeah, thank you. So it's a very interesting question, and my answer is there is no one optimal wavelength. It really depends on a lot of parameters. One of which is your budget. The other one is so we it also looks at where's your satellite going to be, and what are you trying to what rates are you trying to accomplish. So we did an extensive analysis for our mission. For example, we try to take into account all that we could, like atmospheric effects and detectors, sources, and all those kind of things, put them together. And then in our case, 785 nanometer emerged as a local optimum. But I will say I was pretty surprised myself. From UV to 1500 nanometer, it was pretty much, everything was pretty much possible. And telecom actually has some real nice advantages, and I see a lot of future there, so the detectors are a problem, but then it has a lot of performance benefits, like one of which is less solar background, and for example towards daylight and other background situations it might be favorable. So there's a lot of pros and cons, but then at telecom you have the detector issue, right? Anyway, so that's just a few comments.
Yeah, no, thank you. Very interesting. Does anyone else on the panel want to add to that as well regarding the wavelength or the transmission there?
No,
I
agree with Tom, and we have got other parameters considered as well, like for example, eye safety would also become an issue because it is optics lasers, and then whether you're working in daylight or nighttime, etc. So I agree with the sweet spot that Tom was mentioning. We are also around the same wavelength ranges.
That's a good point. Thank you. Sorry, did you have something to say, Doug?
Sorry, I was just adding that, yeah, we were in the same sort of ranges as well. So it's just, it's interesting that everybody's kind of coalesced around the same.
Yeah, so maybe there's an optimum wavelength then. So we have a question here that is quite interesting from Ziheng Shang, asking, is there a plan to build a city optical ground station yet? I think what is meant there is to what the expansion of these kind of ground stations are in order to do the communication from using quantum. Do we have someone on the panel who would like to try and answer that one?
I mean, basically, depending on the type of orbit or satellite that you have, you can have scenarios where with one satellite you can basically achieve or have a global connection with an audio satellite that overflies in a polar orbit. Many options for ground stations, but I'm not sure if I understood the question correctly. So the idea was.
I think that was pretty much answering what was meant with that one. Ziyang was also answering in terms of daylight nighttime. What will it only be operated at night for background subtraction, or what happens in the nighttime?
Okay. So, yeah, I'll give a quick answer. I think daytime operation is a big topic. Many groups are looking into that, and there's actually many interesting approaches out there. I do believe it's possible and feasible. But I will also say, for example, our mission, we did not consider that a priority at the moment. That's why we didn't focus on it. But I think it is technically doable. There's a lot of really good approaches, both on the optimizing the optical link, the spectral filtering, and other things which can really enable that, and the wavelength choice.
Yes, of course, that's an important piece as well. Go ahead, Mamata.
Just adding to that, so I'll explain what we are doing and why we chose nighttime passes. So basically, pointing is one of the key challenges with this technology, and the way we have the system set up is the ground station has a laser which is looking at the spacecraft, and the spacecraft as another laser, and so they have to see each other, and it's a lot simpler in the dark, and it is easier to spot the light, and also so because it involves the visible spectrum, that is a more feasible option, and that's the reason why we went with nighttime passes, and also the wavelengths that we have chosen match with that.
Okay, and were your wavelengths very similar to what Thomas was explaining as well?
Yeah.
Okay, we have another interesting question here from Steve. With all the different satellites and ground developments, how will communication standards be assured, and who is driving this?
I'll take that one.
So maybe I can comment on that. So with respect to quantum key distribution, there is a lot of standard or within the common standard associations, there's a lot of effort going on. For example, there's the ETSI standardization group on QKD, there is an ITUT group, and there is an ISO group, and they all are they are intensively working on establishing the necessary standards for these topics, mainly so far with a focus on also terrestrial topics, but also with future ideas in the area of space-based activities.
Okay, thank you.
Can I add on? Just add on to
Yeah,
that?
absolutely.
In terms of commercial operations, there's actually a huge number of things that we have to consider, and this is the focus of one of our current programs. So yeah, there's the QKD standards coming out of ETSI are really useful, and also the ISO efforts. Also looking at standards for security within organizations, 27001, and also looking at space-based standards. So there's actually quite a lot. So we're trying to split this and come up with a framework which covers not only the quantum key distribution domain, but also the space domain and the cybersecurity domain. And yeah, it's very difficult at the moment. I think in terms of what commercial organizations have been doing, is that they've been coming up with their own frameworks, which kind of pull all of these ideas together. I'm not too sure others on the call might have some views on that, but I think that's kind of the direction that we would look to take on that.
Okay, would someone else on the panel like to add to that? So we have another interesting question that is sort of related to that. So from the system side of things, what do you think needs to be improved on in the small sat industry to enable quantum technologies to orbit sooner?
So that, oh, I can take. So basically, we are using CubeSats because they are good and easy for a technology demonstration satellite, and they are inexpensive. And so because they are very limited with the resources that they have, it is difficult to have, like, for example, the pointing accuracy that we would need, or the stability that is required for the optical comms, and also the eye precision knowledge that's required. And it has power restrictions, mass and volume restrictions, so you have to use the space and volume very carefully. So that's one side of it. And the next one is also on the radiation side. We probably not take radiation into take too seriously with small sats or CubeSats, but again, this would damage or increase the rate of dark counts if the detectors are exposed to the radiation for a longer time. And the temperature variation is another challenge because the APDs that we use need to have a balanced temperature in order to detect the photons properly. And so that is another challenge. Along with that, there is other things like weather and atmospherics. They also play an important role. But again, that's a challenge, whether it's a bigger satellite or small satellite. So definitely there is the pointing stability that we have at the moment for CubeSats are not sufficient enough. So there might be more work around that's required. So in our project, we are using coarse pointing along with the fine pointing mechanism in order to achieve this high pointing accuracy that's required.
Okay, thank you. And Iman, did you have something to add to that?
Actually, just to add to what was said, of course, the real attraction for building small satellites is that they're cheaper to build. But if you do need very fine pointing, you almost have to redevelop the pointing technologies for the smaller satellites. So on the one hand, bigger satellites are becoming smaller. Very small satellites are becoming bigger to make them useful. So there's a magic region where the two will never meet, but they will get closer to each other. So I think this is one of the takebacks or the take homes that you can take from discussions on how small you could make a satellite, how big it really needs to be. And I would say that it's driven entirely by the payload, and of course, but then while the payload might be tiny, the platform to be useful must have a minimum size to be controllable.
That's a very interesting point, because often I see in the satellite world that everyone's trying to make it smaller and smaller and smaller. That's an interesting point, that maybe sometimes it's better to be a little bit bigger in terms of the payloads and so on. Okay, so we're unfortunately going to have to wrap up, and I would just like to see with the panel if everyone could just give a quick couple of words before we say goodbye for this webinar. So let's start with Mamata.
I would just like to add, it's exciting times, and it's a new challenge for all of us, not just with quantum technology experts, but also for space domain. So I'm just enjoying my time working on these missions.
Sounds good. Great. Thank you. How about Thomas?
Yeah, thank you very much. It was actually fun to be part of this discussion and hear the very great discussion from everyone. And yeah, it's exciting times. It's really great. And I think the missions we're working on right now, which will go up in the near term, are just the first step, and there's a lot more to come afterwards. And already, also on our side, we're, for example, already thinking about what is going to be the next generation of satellites and missions. So, but thank you very much, and it's very exciting.
Thank you. And Bettina?
Oh, so I'm but basically not. Oh, yeah, unmuted. Not that much to add actually from my side. I also would like to thank you for organizing that interesting discussion. And yeah, I'm also curious on what the future will bring and how long it will still take until the really next interesting missions will then actually be brought to space. And yeah, nice to have been here. Thank you.
Thank you. Yeah, we're definitely living in an interesting time, and there's going to happen, a lot of things are going to happen in the next 10 to 20 years. Iman, do you have some final words to add?
Yeah, I think it was a very nice opportunity to discuss these things. And I think this is a young person's forum. I think it's important that young people get interested in this and really drive the area. And the area being the impact of quantum technologies in space will be the pure gravitational environment from the point of view of what can be done in space, what can be improved by putting it into space. And then there are the other aspects which we mainly have concentrated on for the last 45 minutes is more on the need to put those things in space, like QKD must go to space to be tested. So with both things together, I think we can make and continue to have very interesting experiments, interesting science, interesting technologies, and move forward.
Thank you for that. And then Doug.
Yeah, I'd just like to say the thing that's stuck out for me within the quantum community has been the way that it's funded to support collaboration, not just between academia and business, between academic institutes, but also between organizations and kind of organizations looking to develop capabilities. So yeah, that collaborative effort has really come out of the academic institutions and continued into the business domain, but which I think has been really positive. So yeah, I think that's my one takeaway. So yeah, and thank you to everyone for organizing today. That's been really good, and I know it's been a lot of work, so thank you to you all.
Thank you, Doug, and thank you to everyone on the panel and the organizers and everyone on the audience as well. I'm sorry I wasn't able to go through all of the questions, but if you do have more questions, please reach out to Kraft Prospect. They're on social media pages and LinkedIn, or you can drop them an email at info@craftprospect.com. So thank you for joining us today. There's going to be more of these webinars in the future, so please keep an eye out, and have a nice day, everyone.
Thank you.
Thank you.
Thanks. Bye.
Bye.
Okay, thanks very much.
Thank you. Thank you.